Hello, everyone. Thank you for joining us once again for vLLM Office Hours, 37 sessions in. Super nice to see some familiar faces, of course, repeats, and then also everybody new. Welcome. This is your safe space to ask any questions. No question is off limits. We're excited to have Kim and Kimbo here from the SemiAnalysis team, the team behind InferenceMAX. So we'll learn all about InferenceMAX. If you are addicted to X like I am, or Twitter, you see there's a lot of always some arguments, questions, and things going on around AI benchmarks. Well, InferenceMAX is here. We said a lot of those, so we'll learn a lot about the project and also some benchmarks and how they collaborated with vLLM. I'm also joined by Michael. Michael actually recently proved that the world, in fact, is round. He boarded a plane in Boston, flew west through Asia into Europe, back into Boston. Michael, how was your trip?
It was great. I think, yeah, we did 2 meetups, one in Beijing and one in Zurich. And yeah, definitely China is strong, and the people there are great to work with. So yeah, really happy about the community we have in both China and surprisingly Switzerland. Strong show of force in Europe.
Yeah. I joined Michael in Switzerland. We had almost 300 people in seats. Amazing meetup. We'll actually have a slide on it. And then in China, week before, there was about 41,000 people who joined the meetup virtually, 315 seats. So it's the community, vLLM community in China is strong as ever. So excited to see. All right. So Michael, I can't do the next slide. Can you do it for me, please? Perfect. So I'll do a couple of things, Michael, and I'll pass it to you for the rest. So yeah, really excited to have the InferenceMAX team here this week. We'll take a break in 2 weeks. It is Thanksgiving on the 27th, so we'll take a break. And then we'll be back on December 4th with the team NVIDIA to talk about how they optimize the Nematron H architectures in the vLLM. And then December 18th, we'll be talking about the speculators library that's about to launch. It's launched already. We'll be doing an official announcement either today or next week. But we'll be digging deep into that one as well. I do want to just call out that LM Cache, another open source project. They are doing office hours. They try to do everything they can to not do it the same day as us. But unfortunately, today it fell on the same day because we've been changing our schedule because of all of this travel. But I did link it here, and you should have the slides so you can actually check out what that's all about and join them. We have a decent amount of meetups coming up. So there's one in India happening this Saturday. Paris next week, Bangkok next week, Malaysia in December, and also San Diego for NeurIPS. So we'll be throwing a vLLM party at a fun arcade place. So if you're going to be at NeurIPS, sign up, come join us. Michael and I will be there, and many others, of course, but come say hi. Michael, I'll pass it over to you.
Cool. Thanks a lot, Sasha. And yeah, hello, everyone again. Unfortunately, we don't have a vLLM release to give you. We're still working ahead on that. Xformers has been a really annoying blocker for the release, but we're hoping to put it out later today. So we'll cover it in the next office hours. But at least I can cover a lot of blogs and announcements and collaborations we've had within the community. So we'll go through that after covering the meetup and what vLLM is. So yeah, as Sasha already mentioned, we had a meetup in Zurich last week, and that was really successful. The first official meetup in Europe, over 200 people, and yeah, great presentations from Red Hat, IBM, and notably Mistral. They had 2 presentations actually, both on their reinforcement learning pipeline and their disaggregated serving at scale, both utilizing vLLM for the inference side. And the whole meetup was recorded, so you can watch all the talks, but I highly recommend watching the Mistral talks as they're particularly interesting, and they share quite a bit for Frontier Lab. So pretty cool to see. Next, just like towards an introduction to vLLM, if you're not already familiar, it's the fastest growing de facto standard in open source model serving. It's a Apache 2.0 LLM inference engine, over 60,000 GitHub stars, over 1,700 unique contributors. I think we have like over 800 PRs a month, and we try to merge most of them. Yeah, so it's obviously a very, very active project due to the amount of models it supports. and the amount of hardwares it can deploy those models on efficiently. Of course, getting good performance on NVIDIA hardware, but offering the software abstractions and working with the hardware vendors themselves to support these models across a variety of AMD hardware, Intel, Google, AWS, Huawei Ascend, Meta X, Rebellions, all sorts of hardware accelerators around the world. We're happy to work with. And at its core, it's a easy to use Python library that you can just pip install or Docker pull away, and then just deploy models straight from Hugging Face or Model Scope and get access to the many different types of inference optimizations that you need to deploy these very, very big models efficiently, which Kimbo and Cam will cover a bit in the InferenceMAX overview. Now we'll go into some things that are been new over the past 2 weeks. This is a blog on the vLLM website covering a feature that we actually had for a while, vLLM sleep mode. This was actually introduced most notably for co-located reinforcement learning or training. So we can share memory between vLLM for inference and whatever training process you're using and not need so many GPUs. But this is actually a useful case for deploying multiple models on shared GPU resources. So here, this blog goes through a lot of benchmarks and use cases, but here it's just showing running a Qwen 3 235B MOE and running a Qwen 3 Coder 30B MOE, and using the sleep mode to start up the first server and then put it to sleep, and then start up the second server, all in the same both in different processes, and then running some benchmarks or workloads on each, and then constantly switching between the models like you would in a service where you're switching between different models based on workloads. And so this allows for serving on just the same number of A100s. And since we don't need to completely kill the server and restart it, we just can offload the weights to CPU memory. We're able to get really much faster switching between models, which is really important for cost-efficient inference where you don't have that many GPUs and you're trying to support many different models, which we definitely know from businesses that have like 100 different business units all with their own models. They don't have that many GPUs yet. So yeah, check out the benchmarking if you're interested in how efficient the feature can be. And actually, we would love some improvements here to make it even faster, as there's clear improvements we can make, like parallelization. Another blog that came out is about the vLLM semantic router project, which recently had a big release, most notably supporting LoRa in a variety of different ways. But most importantly, allowing for like multitask LoRa, so you can help your semantic routing become even more, let's say, like complex and using like multiple models at once effectively by using multiple LoRa adapters. Just getting that in essentially one inference on one model, just as a small LoRa batch using the batch LoRa support we have in vLLM, along with a variety of other enhancements, especially in the between the Go layer and the router layer. So yeah, if you're interested in semantic routing, the project has had really surprising growth under the vLLM project. Recommend you give it a try if that kind of feature is interesting to you, which it seems like a lot of people are post GPT-5. Next, I want to cover some of the key model releases. You already know about these, hopefully, with the Minimax and latest Kimi K2 models. These have been state-of-the-art agent and code models that have been really cool and great to get D0 support for in vLLM. But one really key feature that we added in vLLM now that these open source models are now capable of it is interleaved thinking with tool calling. So adding like first-class support for a model to have both, its tool calling parser and its reasoning parser, and within its thinking, doing a tool call, getting the result of that tool call, and then continuing thinking. This was sort of supported, within like GPT OSS through like the responses API. But now through these models being, fine-tuned and trained to use just the simple chat completions API with this interleaf thinking style, we're able to support these for both these models and hopefully more models in the future. So I recommend checking out the docs page where, we cover how this feature works, and hopefully people can build more complex workflows on top of these more capable models. Next, I want to highlight a blog actually from the Cohere infrastructure team. They wrote a blog, I think they released it like yesterday or the other day, on a feature that they landed in vLLM a month or so ago. This is essentially like optimizing particularly like multimodal inputs in vLLM. So with vLLM v1, we redesigned the core and front end of vLLM to not just offer like prefix caching for text-only data, but also for multimodal data. So we have the ability to cache multimodal data at the server and input processing level. So if we have like an image that we've seen before, we can skip pre-processing it, like resizing it or doing all those things. We can keep that data around in a cache and the front end. And then also there's a cache in the back end, obviously for the KV cache. But naturally between these different processes on your API server, your engine core, and your GPU workers, these are all different sets of processes that you need to do interprocess communication, or IPC, between in order to move this relatively heavy multimodal information. So they worked on extending this by using a shared memory store in order to improve the performance of caching, which they show on their Command A Vision model on the Vision Arena data set. They're able to get almost like a 2x improvement in throughput on the baseline, which is really cool that they're able to do these optimizations in open source that they're able to use in their infrastructure. So it's a pretty good overview of the feature in general and why it's important. This is just the benchmarking results. So recommend checking it out. They always write good things and host good talks. So next I want to cover something that actually kind of flew under our radar for a week or so. But we caught on to it yesterday. So GitHub published their Octoverse report on state of open source models, and they really focused on AI infrastructure and developer tools as the most popular projects that are growing on GitHub. And actually, they listed vLLM as the top open source project by contributors, which is pretty sick. I definitely know we don't have the most contributors. There's plenty of other projects like PyTorch that have more, and even llama.cup. But I think it's like a variety of factors, like the amount of issues and commotion and discussion and work that happens on it. So I'm personally really honored to be anywhere close to like VS Code or Godot or Transformers or I think these are like really important libraries. We're just really glad to be up there, and we're really glad to have such a broad community like you folks are a part of. So thank you. Next, and maybe last on my side, we released a blog yesterday on bitwise consistent reinforcement learning between vLLM and Torch Titan. So if you've been following along, we've been working on deterministic inference in vLLM through the vLLM batch invariant command or flag. So now vLLM itself can be deterministic regardless of the load that it's running on, which is important for evals and for RL. But we also need to make sure that the training code in the RL part of the pipeline also matches what vLLM does. They can be deterministic, but they can still produce different results. And so we collaborated with the Torch Titan team to do just that and get bitwise exactness between both the inference code in vLLM and Torch Titan on this Quen model. And you can see, I know it's probably too small, but if you look at the KL divergence graph here, the yellow bar is without the bitwise setting, and the blue line at the bottom is exactly just zero consistent KL divergence across the whole training, all the training steps. So yeah, this is really a great milestone to achieve between vLLM and Torch Titan. Obviously, it's a little bit custom and needed custom backwards passes in PyTorch, as we note. But we're working towards a lot of options there, or a lot of improvements there, and hope we can, hopefully just like raise the standards for reinforcement learning libraries. So more libraries than even just Torch Titan can try and have like unified model code, and hopefully have better on policy reinforcement learning when using vLLM. So thanks a lot, especially to the PyTorch teams who worked on that. Sasha, you have your hand raised.
I'm not used to that, right? Yeah, there was a question in the chat, Michael, about what device is everybody using to make contributions in the vLLM. Bishwa here was trying to build a repo on top of Apple Silicon, but getting a hard time, which is probably expected. Any ideas, how people can contribute without having the state-of-the-art GPUs?
Yeah, I mean, the majority of the work happens on NVIDIA GPUs. You can very much well use like consumer GPUs. Like I personally am able to use like my 4090 on my Windows desktop and work just fine in Windows Subsystem for Linux. Yeah, definitely like the CPU only backends need some love. It's basically just maintained by like a few people at Intel, including like the Mac support. So yeah, I mean, if something's broken with it, would love to know, and if you can help fix it, would love to. You can definitely use the CPU backend for development, but obviously it's more for like functionality and like core features like the front end and the engine core loop, and a lot of the features like CUDA graphs and Torch compile. The focus there and performance is less so on the CPU backend. But you can at least work on like front end features like tool calling support or API server features on the CPU backend. So yeah, I mean, if you're running into issues, definitely come into the vLLM Slack and help us help you fix it. We'll go through more time at questions at the end, but for now I'll hand it off to Kimbo and Chen to go over InferenceMAX.
Okay. Hi everyone. My name is Kimbo. I'm an engineer at SemiAnalysis, and today I'm joined with my colleague Cam, and we're going to talk about our project InferenceMAX. So what is InferenceMAX? First of all, it's an LLM inference benchmark, and it is a good benchmark. And so the key points to InferenceMAX is real time, it's practical, cutting edge, and open. So what I was describing was trying to tackle some major problems in systems benchmark in general. So here I list 4 issues. First, I think system benchmarks usually fail to measure the changes across software versions, because software cadence is for AI is usually at a biweekly to monthly cadence, but systems benchmarks are not done that frequently. So InferenceMAX, we chose to do continuous updates. Right now, we're doing almost nightly updates, and by doing so, we can benchmark the differences between software versions and show the performance improvements over time. The second issue we see is that systems benchmarks usually have setups that are kind of impractical to replicate. So if a user wants to use a good server configuration, it's usually very difficult to get the exact commands and get them running. InferenceMAX is different on this side. We use open source software, which includes vLLM. And we try very hard to use reasonable server configurations so that a developer can just directly take those configurations and use it. The third problem is the AI field moves so fast that it's hard for system benchmarks to keep up with state-of-the-art techniques. InferenceMAX also strives to keep the benchmark updated. For example, our current benchmark is benchmarking state-of-the-art techniques such as P disaggregation and also large-scale expert parallelism. And we are continuous updating to get more features like this. Finally, I think system benchmarks usually have very detailed and complicated rules, and they're sometimes a bit opaque. InferenceMAX is very transparent. All our code, benchmarking code, is in a public repo, and the design is fairly simple. You can just replicate the performance results by just pulling the scripts and run it on your server locally. In addition to those 4 main points, we also think InferenceMAX has some unique features. First of all, InferenceMAX plots the full throughput and latency curve. In addition to that, in addition to throughput and latency metrics, we also have interactivity and some metrics that are more industry-oriented, such as TCO, the price per token, the tokens per megawatt. And coming soon, we'll have MFU and teraflops. For the industry-oriented metrics, we are using our own data center industry model and the cloud TCO model to perform those estimations. So if anyone in the audience is interested, please contact sales@semianalysis.com. So one thing I like to highlight about the reason why we plot the full latency and throughput trade-off, throughput curve, is because throughput and latency is essentially a trade-off. At high throughput scenarios, typically at those scenarios, the server can crunch through a fixed number of tokens at a less amount of time. And since GPU machines are priced by the amount of time you use, that translates to lower cost. But at the same time, because higher throughput, you're batching higher, it takes longer for the GPUs to perform matrix multiplication, and in the end would lead to higher latency, and users would have worse experience. So I think everyone can relate to ChatGPT and maybe Claude taking too long to respond, things like that. The other end of the trade-off, which is lower latency, it would have the opposite case where you have a better user experience, the response is snappy, but because on the server side, it'll cost a lot more because it'll take longer for the server to serve multiple requests and leading to higher costs. An analogy would be high throughput is kind of like a bus where you can take a lot of people. The single user experience is not that great, but it's cheaper. Whereas low latency is kind of like sports car. where every person, the car can sit only maybe two people, and the seat is a lot more comfortable than maybe buses, and it goes very fast, but it costs a lot more. Oops. Okay. So I'd like to talk about a bit about our benchmarking methodology, specifically how we set up the benchmarking client. There are three main principles. First, we want to minimize our dataset dependency. This is due to our limited resources and time. We want to present performance results are served kind of like as a baseline, and make the results more widely applicable. So because of this principle, we chose to use random tokens instead of data sets to remove some dataset dependency. And also, we disabled prefix caching because prefix caching, the ratio is highly dependent on your serving scenarios. The second principle is we try to measure the steady state of the performance. So first of all, because of this, we disabled the dynamic request rate, which typically is sending requests following a Poisson distribution. Instead, we do infinite request rate, i.e. dumping the whole set of requests. But we limit the maximum concurrency so that the server is processing requests at a max number of requests. The second thing is we scale the number of prompts with the maximum concurrency. So for example, if we set a concurrency at 32, we would, let's say we have 320, 10 times the number of prompts. If we increase the concurrency, we would also increase the number of prompts to make sure that under every concurrency, we are allowing the server to process a sufficient number of iterations so that it reaches a steady state of the performance. Finally, we are coming soon. We are adding a more extensive warm-up phase because we are seeing some differences in servers that would benefit from having like let's say like a 10 requests or some number of requests for warm-up. Finally, we are trying to simulate real-world request lengths. Since in real world, the input sequence length and the output sequence length are rarely constant. It is usually a distribution. So right now we are doing, what we do is we randomly vary the input sequence length and the output sequence length to a certain ratio. And we use this flag in vLLM benchmark scripts called random range ratio. And the flags, what I mentioned can be essentially boiled down to this code snippet down below. And one thing I want to mention is we are really thankful for vLLM having a great benchmark serving script. We based most of our benchmark serving on vLLM script. So yeah, thank you, vLLM team. Okay. Finally, I want to talk about InferenceMAX thrives with open source, thrives with the community. We benchmark the systems using open source software. So we improve the open source software and try to improve the default user experience. Some examples of how we do this include, first of all, we push to use official Docker images. We try to get the companies to reduce the usage of specialized images. And also we are trying very hard to convince AMD to upstream their code back to vLLM, and hopefully in the future, vLLM Docker image, the vLLM Docker repo can have all the GPUs, all the different hardwares. The second, we try very hard to reduce the server configuration flags and the environmental variables. We've seen people complaining about vLLM server configurations are massacred by the AMD setups where they have like 200 environmental variables doing all kinds of things. And we don't think that's a sustainable and good user experience. InferenceMAX, throughout the past couple months, we are working with vLLM and working with AMD to improve the default configurations. I think NVIDIA's some of the serving configurations are upstreamed, and AMD is also coming soon. And we also helped with vLLM in creating vLLM and NVIDIA in creating some serving recipes, showing users that under what model, what scenario you can use what kind of configuration flags. Finally, in the future, we want to try to upstream more of our improvements on our code back to the community. As a first step, we've made a PR on vLLM and upstreamed our warm-up code back to the vLLM repo. And we thank vLLM team for reviewing and helping out and merging this improvement. Okay, and I'll leave it to Cam to talk about the InferenceMAX detail architecture and the future features.
Yeah, hey everyone, thanks Kimbo. Yeah, I'm Cam, also an engineer at SemiAnalysis. I'm very happy to be here today. Like Kimbo said, I'm going to talk a little bit about kind of the actual architecture of InferenceMAX and how we set it up. So we use GitHub Actions, and as you can see here, we have 3 top-level workflows here. We split it up by full sweep scheduler, 1K, 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 8K, and 8K, 1K. The reason we do this is because GitHub Actions actually has a limit of about 500 jobs per workflow. And yeah. One sec, sorry. Sorry about that. What's up?
Is everything okay, Cam?
Yeah, can you take over for 1 sec? I'm sorry.
Yeah, sure. So this is a description of the detailed architecture of InferenceMAX. Basically, how InferenceMAX is set up to do an automated benchmarking. First of all, we use GitHub Action workflows. It is a software or a system that allows automatically triggering jobs. And this graph shows the current details of the steps you go through in launching a job. So at the top of the workflow, we have a full sweep scheduler. That means in this workflow, we benchmark all possible configurations that are serving at the input sequence length 1K and output sequence length 1K. And so we can see we have 3 such workflows with different input-output sequence lengths. For under one scheduler, we have different setup jobs. Right now, the jobs are first split by the model types. Here we have DeepSeek R1 and GPT OSS. And under those jobs, we have ways to parallelize all the configurations of different sets of concurrencies and different sets of detailed server configurations, such as like tensor parallelism. And for DeepSeek R1, we might have more advanced features such as DP, a data parallel attention, etc. And these are done by a feature called matrix strategy in GitHub Actions. Finally, they all call a template of benchmarking that is parameterized as general as possible. We call it benchmark template. And these benchmark template are called based on the configurations, the jobs sent. And then we collect the results, aggregate them, process them, and then we show it in InferenceMAX dashboard.
Yeah.
So this is
Kimbo, I can take back over. Sorry, I just had to step away for a second.
okay.
So yeah, so this is the InferenceMAX current architecture here. As you can see, this is basically describing the same thing we described in the last slide, but this is the actual GitHub action workflow. Right now, we also split up GB200. So GB200 is like second class right now. A main priority that we have open right now is making multi-node inference like first class within our repo. So that's another thing. So as we add, PD disaggregation and YDP, stuff like that, those are all going to run multi-node. So we're really going to want to make that first class. Yeah. So now we kind of want to go over some of the results from InferenceMAX. And we really want to highlight the improvements that have been made, particularly from vLLM 0.10.2 to 0.11. So as you can see here, right, this is GPT OSS with 1K input sequence length and 1K output sequence length for H100. The blue line is vLLM's 0.10.2, and the red line is 0.11. So as you can see, there's a significant improvement here between the versions. So yeah, we really want to recognize vLLM for making great improvements here. Let's see some more results. So yeah, this is also 1K. This is showing cost per million tokens. So as Kimbo mentioned earlier, this is using SemiAnalysis TCO model, plotting cost per million tokens on the y-axis versus interactivity on the x-axis. So this shows here that vLLM upgrade actually makes inference cheaper as well, which is nice. Moving on here, we also show the end-to-end latency graph. So this is throughput versus end-to-end latency. So vLLM is faster in 0.11 as well. Keep going. Kimbo, if you have any comments too, feel free to add. So here we're showing 8K input sequence length instead of 1K input sequence length for total throughput versus interactivity. Still, version upgrade is faster across the board. What else? Oh yeah, I wanted to throw in, we also have token throughput per all-in utility megawatt. So this is power, also using the industry model from SemiAnalysis. So vLLM 0.11 is actually more power efficient as well. And this is showing total throughput versus end-to-end latency for 8K, 1K. Okay, here we have H200 results. So while not as pronounced, still there's still improvement from 0.10.2 to 0.11, particularly at low levels of interactivity, which is important for some use cases. Let's see what else. So 8K, 1K with input sequence length, it gets more pronounced, the improvement. Here's end-to-end latency again. So significant improvements in latency. And yeah, that's it. I can go talk about any of the results that anyone has questions about at the end, but let's see. So yeah, we have all these results come from the a preview of our new and improved front end for InferenceMAX. So with this new and improved front end, you're going to be able to compare dates across all different frameworks and all different GPUs. So I can say, how is vLLM improved basically from, October of this year to November of this year? I can look at multiple different GPUs. I can say, how does H200 compare to MI325 between these two dates? So as Kimbo was mentioning earlier, as software and hardware is improving at such a fast pace, being able to compare across dates is going to be really important. So we're also going to add some high resolution graph exporting and a lot more features that I think you all will find extremely useful. And we're also planning on open sourcing the front end at some point. But in the meantime, if anyone has any suggestions on free features, you can go ahead and open an issue. We're always open to feedback, and we're trying to get features out as quickly as possible. So yeah, that brings us to this point.
Cam,
yeah.
Cam, would you like to share your screen and just show the front end dashboard and just click around and show everyone?
Yeah, that's a good idea. I'm wondering, should I? Yeah, I'll show.
Yeah, sure. Let me just stop sharing and you can take over.
Yeah. You guys see my screen?
Not yet. Yes.
Yes.
Yeah.
Okay. So unfortunately, like I said, the views I showed in the slides are a preview, but this is the actual production website. You're not going to be able to do the comparison between dates, but yeah. So here you can select a model. Right now, either GPT-OSS or DeepSeek R1. Then select an input sequence length and output sequence length. You can select a precision for models that have multiple precisions, such as DeepSeek. And then here, I think this is something we've touched on a lot, which is really cool. You can select different y-axis metrics. So, power. You can select many different TCO scenarios. So for instance, this one is hyperscaler owning, and this is owning for a neocloud giant, and then this one is just like a 3-year rental. You can also enter your own price per hour per GPU. So for instance here, if I disagree with this price for MI355, I can make it 300, so you can see the difference. And you see it'll update the graph here. So that's a very expensive GPU. But yeah, and then also there's interactivity down here for a different x-axis. And then, this is another thing that we think is pretty cool. So this is the quote unquote reliability graph. All this is doing is for each SKU, it's calculating how many runs were, the percentage of runs which were successful. So yeah, this might not be perfect for like actual reliability since our sample size is relatively small, but we believe it's a good proxy for the reliability of these systems. So yeah, missing a few dates here, but yeah, so that's pretty much it on this end. Let me stop sharing my screen. Oh,
yeah, one
sure.
final thing.
Yeah.
Just please consider, if you find the repo nice, please consider start the repo. Yeah, we need the GitHub stars.
Yeah, sure. And I'll share the link for the repo in the chat.
Oh,
It's on
thank you.
GitHub.
Thank you. We're like YouTubers, like and subscribe.
Yeah. Shameless plug.
Of course.
I think Ravi, you had a question.
Just a quick question. I mean, on the results, because I was just thinking from perspective that there's so many use cases right now, right? I mean, you're multimodal, you're agentic, and so on, and then of course there's all the distributions that you use for the ISL, OSL, and so on. How does the user try to see, I mean, if this particular graph makes sense in this particular use case or not. And also the other question was that basically when there are two releases, you show, okay, the Pareto kind of the frontier kind of improves. Is there something to say exactly why that happens? Or is it just saying that, okay, you just have to refer to the blogs and so on to see the reason for that?
Yeah, I mean, I think vLLM switched to full and piecewise for the CUDA graph default. I don't know if that, in what part, to what extent that was responsible for the improvement, but Michael can probably talk more about that.
Yeah, I mean, definitely that's probably like the biggest standout feature, but yeah, I mean, that doesn't help you so much in throughput scenarios. So like, and there were like improvements across the board. So yeah, I mean, in a given release of vLLM, it's like, you know, hundreds of commits like every release. So it's a bit hard to pin things down. I think, yeah, I mean, my opinion is like, it's maybe not like so important that like how the software is getting better, but that the software is getting better. And I think like things I'm looking to see out of like the future of something like InferenceMAX is like, is it getting better across like all hardware platforms? As you showed already, like there's a pretty wide variety of, you know, NVIDIA and AMD hardware and hopefully more, but also generations of that hardware that, you know, we can sort of see that like, oh, you know, maybe H100s didn't really improve much at all, but like, you know, B200s have like, you know, gotten 50% faster or like 70% faster over like a time period. And I think that's one of the things that's maybe most important for like, yeah, something like this to show, because I think something like InferenceMAX is useful for people that are deciding if they should buy the latest and greatest hardware, and if like the software is ready to utilize it well, and sort of how the open source software that are the standard things that most people are going to be grabbing off the shelf when they get their new hardware and trying to run it, like, is it ready to take advantage of that hardware yet? You know, these things are not scaling as well on like real workloads that like the spec sheet says in terms of like pure memory bandwidth and flops from like a B200 to an H100. But you know, the software is trying to get closer and closer to that. And yeah, like hopefully something like this will detail like that readiness of the ecosystem better. Yeah, that's my thought.
Yeah, thanks, Michael. The other question was related to, I mean, how does basically for an enterprise user, how do they relate this to I mean, how do you choose the workload profile? You talked about Poisson distribution and certain distribution you use for your sequence length. I mean, is that coming from a particular source or?
Yeah, I mean, I guess, so like, for instance, for sequence lengths, right? Like, you know, like 8K, 1K might be for like coding or something, because for instance, your input sequence length is going to be like a huge chunk of code, or like maybe that would be something like summarization where you're feeding the LLM you know, a ton of context and you get a shorter output length. And then like 1K would be more synonymous with like chat, just like basic chat, not a super long input context length, but not a super long output context length either. And then finally, the last scenario would be like 1K, 8K, which would be something that's really hot right now, which is like, you know, reasoning and like agentic agents and stuff like that, because you have a relatively short input and then the LLM is thinking, generating tokens and iterating upon itself. So that's kind of how you can think of the scenarios in like a basic sense. And then in terms of what Kimbo was saying, you have to decide kind of where you're hoping to serve your model at in terms of interactivity, right? So like, if you're serving very few users, if you want to serve few users very fast, then it would be somewhere on that right side of the interactivity curve. And if you want to serve a bunch of users, then it would be somewhere on the other end, right? So I think those are the things you have to take into consideration. Kimbo, do you have anything to add to that?
Yeah, no. I think yeah, Cam pretty much covered it. Like we mentioned in the benchmarking methodology, um, there are a lot of different details to your serving scenario. Um, in addition to what Cam just mentioned, these numbers can serve as like a rough baseline for reference.
Thank you.
Yeah, I think it's a good point. I think there's a lot of yeah, really complex, like realistic workloads that you can cover. Obviously, there's hundreds of them, but you know, it's good to, I think, certainly from like a benchmarking and like profiling perspective, we like deterministic benchmarks as much as possible, not doing wild varying ranges of data where like maybe if you change the order of the data from run to run, it's going to wildly change metrics. So yeah, it's always a sort of challenge, I think, to do realistic workloads and then also get like clear apples to apples comparisons. Yeah, I can definitely say from the optimization perspective, we generally go towards deterministic benchmarks. It just makes it easy to make sure we're making some sort of consistent progress. Yeah. Are there any other questions from folks in the audience? Feel free to raise your hand or come off mute.
Did we answer Chris's question about piecewise?
Oh yeah, the piecewise CUDA graphs are just, you know, yeah, just doing CUDA graphs for regions of the model execution and skipping some operations that aren't compatible with CUDA graphs. So we originally did that in vLLM v1, where we did piecewise CUDA graphs around attention operations. And so you could have some more complex custom attention specialization. But yeah, that hurts low latency. And so now we have support for like doing full piecewise, combining CUDA graphs together. So the default now is kind of both. And we dispatch whenever we're able to do the best thing, whenever we need to be latency optimal or throughput optimal. Yeah, thanks, Chris. Any other questions? Cool. Well, yeah, thanks a lot to the SemiAnalysis team for presenting and covering the project. Really looking forward to the new features and yeah, the consistent progress on it. It's great to have another benchmark to tell us where we need to be better in vLLM. We're very thankful for it. Yeah, thanks everyone here for coming to another office hours. Hopefully you're already a part of the community, but if you're not, we're happy to have you join in and contribute features, give us feedback. Please join the developer Slack. Don't be a stranger. Yeah, tell us about issues or how you're using it, how you're using the project. And of course, if you want to help out, there's a variety of special interest group channels, whether you're interested in multimodality or speculative decoding or tool calling or a variety of different features. So yeah, hope to see you in the community and hope everyone has a good next couple of weeks.
I have a personal announcement. We at Red Hat are building an AI developer evangelism or advocacy team. So if you know somebody or if you yourself love building amazing AI demos and showing them to people and going to conferences, traveling, let me know, please. It's sasa@redhat.com, or you can find me in the vLLM Slack.
Yeah, thanks, Sasha. Oh, David, do you have a question or? No, maybe that was just a click. Okay,